Hello and welcome to Lecture 7, covering Section 4.3 from Survey 10th edition on the topic of projectile motion. Projectile motion is a type of two-dimensional motion, 2D kinematics. In fact, you could use all the techniques of general definitions of integral calculus definitions of kinematics from the previous lecture to do any of the problems in this lecture. But projectile motion is more applied. It's such a common situation. It's good to maybe think about it separately. Good to think about fast techniques of solving projectile motion rather than trying to always do it the most thorough way from basic definitions. Okay? So that's the idea. Is certain situations that are common, we should focus on and learn faster ways of solving them. And that's what we're going to do with projectile motion. Okay? But first of all, what is it? So, projectile motion first requires that we define what a projectile is, because we already know what motion is. It's position, velocity, and acceleration, okay? Maybe velocity and acceleration. But let's define a projectile, all right? So first key term. A projectile is simply any object whose only acceleration is gravity, okay? So that's it. As long as there's in this case, one directional acceleration, because gravity is going to point along a single axis, and it points down, and it has a particular value on Earth of 9.8 meters per second squared, that's a projectile. So technically, things that are in a free fall, like we talked about before in 1D motion, is an example of a projectile. It would just kind of be the boring example, the really basic example. We're going to have projectiles that move side to side as well, but they all experience just that one acceleration of gravity, okay? Projectiles are in free fall, okay? So they're absolutely in free fall because the only acceleration acting on them is gravity, so they meet that definition of free fall, but they can have side to side or horizontal motion as well. Projectiles usually also have constant velocity horizontal motion, okay? So I say usually because it could be that they have no horizontal motion and they'd still be considered a projectile. Now, word of caution or caveat here, there's a couple examples I'm going to do that are included in projectiles because of their similarity, or I should say included in a section on projectile motion due to their similarity to projectile motion that are not actually projectile motion problems. And these are problems that involve the addition of a horizontal acceleration, usually like a rocket thruster, okay? It could also be drag, but that's kind of a problem for another chapter because it's more complicated. Air resistance, that is. Okay, so, kind of warning there, I clearly identify which problems are like that, so you'll see that coming up, all right? So let's talk about the picture of projectile motion, right? Because this is really kind of encapsulates a lot of what we're talking about, all right? So here's the idea. We have the idea of a projectile trajectory. It's simply an arced path through the air. It's a parabola, all right? Gravity acts the whole time, and there is some initial velocity. And the initial velocity is usually going to have an angle measured relative to the horizontal. That's like the launch velocity, all right? And then that velocity vector has components that are also themselves vectors, a vertical and horizontal component. All right. Now there's variations on this, but this is the basic idea. Notice in this basic introduction to a projectile trajectory, the ground is level. So the projectile is going to start at the same height that it ends on. All right. Let's look at the velocity throughout the trajectory. So at first, the initial velocity is v naught. Once the projectile has started to move along its arcing path, its velocity is no longer v naught. All right. Both its angle and magnitude have changed. How do I know that? Well, because by the time we get to the top of the arc, the entire magnitude, which is the velocity at maximum height, is only horizontal. So that means that at this point, v at the top of the arc is equal to v naught x, as I clearly show here, right? So that it's certainly shorter because v naught x was just one side of the right triangle with a hypotenuse that was v naught. All right. And by the way, the subscript, y max, isn't saying that this is a vertical component of velocity. It's just saying this is the velocity at y max at that particular location. All right? Kind of a confusing subscript, I know, but I wanted to make that clear. And there you can see here's that vertical measurement of y max. And then if the projectile comes on its way back down and hits the ground, if it's on level ground, it's going to hit the ground with the final velocity, f for final, where the x component is equal, because in fact the x component hasn't changed ever, okay, throughout the entire trajectory. And the y component is equal in magnitude, but facing the opposite direction, it's facing down. So essentially this final velocity vector is just this initial velocity vector reflected about the x-axis. Okay? All right, so that's it for terms and an introduction to what a projectile trajectory looks like. Notice, right, I chose a typical coordinate axis of positive x to the left, or to the right, excuse me, and positive y upwards. Let's look at the formulas. The formulas are nothing new, really. They're just the formulas of kinematics in 2 dimensions and the kinematic equations, which are the equations from calculus that are specific to constant acceleration motion. Because, of course, this is all constant acceleration motion. This is two-dimensional constant acceleration motion, all right? And we're not going to do any 3D projectiles. We could, right? But we're not. We're going to assume we can always look at one plane of motion, and that's our projectile. Because, in fact, the projectile would always stay in a plane. It would require some, horizontal acceleration, maybe in the back and forth direction, to actually create a third dimension. But none of our projectiles do. Okay? So here's the initial velocity in I hat, j hat notation with its 2 components. Here are scalars. And then here's just acknowledging how you would actually find the magnitude of either of those components. And that is assuming that theta is measured relative to the horizontal, which it usually is. Okay, so this is the initial velocity vector. Okay, this idea could be applied to any instantaneous velocity vector as well. So if you found the time-dependent velocity, then you could then find out, break up the velocity at any part of its trajectory into I hat, j hat components, right? For in other words, you could use the same idea of components to say find the velocity at that moment in time. All right, so then let's look at motion in x. So the position and velocity in the x direction is simply these 2 equations. Why are they so simple? Because there's no acceleration in x. Thus, the motion is just x naught plus v naught x times t, because this is constant velocity motion. And this is just saying that the velocity never changes, right? Obviously, okay? All right, because there's no acceleration. You can't change the velocity without acceleration. Okay, but what about motion in the y direction? So this is the position and velocity in the y direction. And then all together, these 5 equations are really kind of the main equations of projectile motion, which just is a specific case of 2-dimensional motion, very specific because it's constant acceleration, and that acceleration only points along a single axis. Okay? All right, so let's move forward and solve some problems. So let me just be upfront that I put a lot of examples in here because projectile motion is important. I'll move through some faster than others. Kind of just mention on the key ideas of how to solve some. Obviously, the full solutions will be available after the fact. I will always spend more time at the first of each type of problem. All right. And the reason I've done this, I've included so many examples, is just because projectile motion is a system that is really easy to have cost of variation on. It's very real life. It has lots of applications. So inevitably, it's something we should talk about in depth. All right, so let's look at the types of problems we're going to see in the practice. Oh, but first let me do one more equation. This equation here, it looks new, but actually it's just derived from the 5 equations that we looked at. Not that we need all 5, but this is just derived from the kinematic equations for projectile motion. And what's happened here is we've just algebraically eliminated time. So we have y as a function of x. All right, so this is the vertical position as a function of horizontal position. All right, so x is the independent variable, y is the dependent variable. This coefficient on x is just a constant, right, because it's just set by the initial velocity of motion. Likewise, the coefficient on the x squared term is just a constant that's set by the initial velocity and angle of the launch and gravity. All right, and really we can rewrite this in terms of showing the angle more prominently, or we can just write it in terms of components, right? So these are just 2 alternative forms. Very useful equation potentially, and also it's an equation that clearly shows that the projectile, so x or y as a function of x, is a parabola. Right? It wasn't that picture I drew of the trajectory, looking like a parabola. It truly is a parabola because we can see that this is the equation of a parabola. So that's kind of cool because that's telling us that the y motion as a function of time is a parabola, and the y motion as a function of x is also a parabola. Okay, what is the x motion as a function of time? It's just a line. It's linear. Okay, all right. So 5 types of problems here. Type 1, problems that involve projectiles launched from and landing on level ground. Right, those are the simplest ones. All right. Type 2, fairly complex problems that involve projectiles launched from a higher or lower point than on which they land. So launched off the edge of a cliff, or launched from a valley up onto a cliff. Type 3, fairly complex problems that involve projectiles ending their trajectory by crashing into a wall or other vertical obstruction. Because that's a difference. Because normally it's the ground that ends the airborne part, that ends the trajectory. But if your constraint, if your ending condition on this trajectory is a horizontal constraint, that's different. It kind of requires a different solution method. All right, and I just want to call attention to that so it's not confusing. So that's a separate type of problem. Type 4, complex problems that involve projectiles landing on sloping ground. Okay, so the idea is that it really requires an extra moment to think about, because how do you deal with the fact that the ground, it's not like you're going from one height to another, you're going from a height to another, but where the other height is dependent on how far you go. So there's a lot of interdependency there. Basically, you just need one other functional relationship that relates y and x, right? Not in terms of the actual trajectory, but in terms of the slope. All right. So I have one example of those, right? And I also put one for practice that you can do on your own. And then finally, fairly complex problems that involve non-projectiles. So I put this last because this is the kind of the exception. These are things like rockets. They experience a second constant or non-constant acceleration other than gravity. Okay, and I said they're not as complex because you can just follow the steps through them. They're very procedural. Whereas type 4 maybe requires a little bit more abstract thought, right? More creative thinking. All right, let's jump right into a nice simple example. A long jumper is running at a speed of 9.39 meters per second when she launches herself off the ground on an angle of 14.5 degrees, so low angle, with the ground. The ground is perfectly level. How much time will she spend in the air? All right, so we're going to use the motion in the y direction as our, kind of our equation to use here. Notice this is the kinematic equation, but it's specialized to gravity. So it's this third term, instead of just being plus 1/2 at squared, is minus 1/2 gt squared. Why minus? Because of the direction of gravity. Okay, so we're putting the minus in there because we've already taken into account that the acceleration is negative g. Okay, all right. It's a word of warning because I don't want you to double count your negatives. Okay, so then we're just going to solve for t. We set y equals to y naught because it's level ground. So then we have a very simplified form of the quadratic equation. All right, and there's two solutions to that equation. Either t equals 0 seconds or t equals 2 times v naught y over g. Okay, so this would be a symbolic solution to this quadratic equation. I haven't plugged in any numbers yet. What does it mean though for the solution to be 0, and how do I know that's a solution? Well, I'm doing here is I got negative v naught y, and then I'm plus or minusing the square root of v naught y squared. Well, what's the square root of v naught y squared? It's just v naught y, right? So in other words, if I have negative v naught y plus v naught y, that means that the numerator is 0, and that's a solution of 0 seconds. Well, that means that one of the times it takes her to hit the ground is 0 seconds because she started on the ground. So that is a solution, but that doesn't really count because she hasn't actually jumped yet. Okay, so the actual real solution is this one. It's the time she spends in the air. And when we plug in our numbers, we end up with 0.48 seconds. All right, not very long. And this is not going to be the maximum time she could spend in the air. We could get more time airborne if she jumped at a steeper angle, but she wouldn't go as far. And actually, we could even get a longer distance if she didn't jump so low. If she jumped at an angle closer to 45 degrees, she could maximize her distance, which I suppose is what she's trying to do. But maybe she's not a very good long jumper. I'm not sure. Okay, so how far will she jump? So now we're just going to use the time that we found. So this is a very important idea, and you'll see this is the first step in a lot of projectile motion problems. Find the time that the projectile spends in the air. Because once you know that time, then you can plug that time back into other equations to find other bits of information. Case in point, question B, how far will she go? All right, so I just take the x naught, which is 0, because I just set the origin of the jump at where she becomes airborne. And then v naught x is just v naught cosine theta, and that's because we're measuring the angle of 14.5 degrees relative to the horizontal, right? Like so. All right, there's our theta. All right, and I just found the x component, right? And then I'm multiplying that by t. Well, if I plug in t symbolically, it's 2 v naught sine theta over g, which means the distance that she goes is 2 v naught squared cosine theta sine theta over g. This actually is an equation that often comes up as the range equation, right? But I'm very hesitant to put that in an equation that I would include in the key formula section. In fact, I wouldn't do it because it's specific. It's specific to a jumper or any projectile that is shot over level ground. In other words, that begins at a height and ends at that same height, all right? But that is the range equation, so-called, and we can see it's dependent on the magnitude of the initial velocity, the speed, the initial speed, and then both cosine of theta and sine of theta, right? And this is the value, x, is maximized when this equation is at 45 degrees. So in other words, to maximize this equation, you can find that theta has to be 45, okay? But in this case, of course, it's not 45, it's 14.5. All right, and plug in our numbers, and we get a range, a horizontal distance covered while airborne of 4.36 meters, which is actually really far, but that's because she may not be the best long jumper in terms of getting her angle right, but my God, is she fast. 9.39 meters per second is like record-breaking sprint speeds, okay? But humanly possible. What is the maximum height she reaches? Okay, so how do we find that? Okay, well, we use V equals V naught y minus GT to find the time to y max, and y max equals this, okay? So that's how you would do it, okay? If you wanted to. But you can also just cheat. Well, not cheating, it's being smart. Or you can use symmetry of the jump to find the time to max height as half the total time in the air. Because it has to be. There's no asymmetry. The time it takes her to get to the maximum height has to be half the jump. And we know that the total time of the jump is 0.48 seconds. That means that the answer to part C just has to be 0.240 seconds. It has to be. Okay? All right, finally, D. Now, D is an interesting question. All right, it's more specific. What is the height of the jumper when her velocity vector makes an angle of 5 degrees at the horizontal? On first pass, this might seem like, oh my God, how would you even answer this question? But it's all the same stuff. It's all the same ideas, and it's actually not hard to answer. So the first thing you want to do is you want to find out what, maybe how long it takes to get to 5 degrees, what's going on at 5 degrees, all right? I'd say probably the most important thing is just find out the time it takes until the vector makes that angle with the horizontal, all right? So what do we know? Well, we know that the horizontal component of the velocity is unchanging. It's just equal to the initial horizontal component of velocity. We also know that at any point in the jump, tangent theta equals the vertical component over the horizontal component, right? At any point, that would apply to any instantaneous velocity vector of the jump, okay? Thus, we can say that Vy is time dependent, okay? I'm sorry, not yet. We're going to solve for Vy. Vy is just equal to V naught x times tangent theta at any point, right? So in other words, this is the vertical component of velocity at any point as the function of the initial velocity, a constant, times tangent theta, a variable, okay? So then I'm going to go ahead and plug it in. I'll plug in the 5 degrees, okay? So look what I'm doing here, right? So I take V naught x. Well, V naught x is in terms of theta naught, the launch angle, and the initial speed, okay, the initial magnitude of velocity. Tangent theta is in terms of the variable theta. So notice there's two thetas. There's theta naught, the launch angle, and then there's the variable theta, which is 5 degrees. All right, so I'll plug in both of those as well as the original magnitude of the jump, 9.39. All right, and we get a speed of 0.795 meters per second. Okay, now I said one good way to find this would be find the time it takes to the angle happen. But here actually instead, I found it because there's often more than, I should say there's always more than one way to solve these problems. Because the equations are so interconnected, you can go about it different ways and still get there. Sometimes you can take a longer route and solve for numbers you didn't need, but it doesn't matter because you will still ultimately solve the problem. All right, it's not a race. It's just a matter of finding out how to do these problems. Okay, so there we just found then the velocity, the vertical component of velocity when the jumper is at a 5 degree, when their instantaneous velocity is at a 5 degree angle to the horizontal, right? 0.795 meters per second. All right, then we're just going to use this equation, which relates the vertical component of velocity, the instantaneous vertical component of velocity, to the initial vertical component of velocity minus gravity times height. Because now we can just solve for delta y and we're done, because we were asked for the height of the jumper. Now again, I could have found the time and then plugged the time back into the vertical displacement formula. That would have worked just as well, okay? But since I didn't need time, I skipped over that. All right, so then we're just going to solve for delta y. That corresponds to a particular instantaneous vertical velocity that we found, as well as the initial one. Plug in our numbers, all right? All right, so here we have, okay, so we've got, right? So we're just going through. Oh, notice I switched the order here. So this right here is V naught y, but I put it first. Why is that? Because I multiplied the whole thing by -1. You can see that I multiplied the whole equation, well, I should say I multiply it by -1 over -1, which is the same as multiplying by 1, which doesn't change the equation. And I did that because that way I got rid of the negative in the denominator. Notice that, right? So in other words, I swapped the order of the two terms in the numerator. Okay, so this is just V naught y, and this is Vy. And we know this is Vy because look. Okay, so notice my algebra there. And then we just find our answer, 0.25 meters. All right, So that is how high she is when she's at a 5-degree angle, okay? And this is actually pretty close to her maximum height. Find her maximum height. It'll be slightly bigger than this. All right, cool. Let's move on. All right, so got a couple of problems that don't involve level ground. All right, so first one, launching something from a plane, having it take a parabolic path down to the ground below. An Alaskan plane drops a package of emergency rations to stranded hikers as shown. The plane is traveling at a horizontal velocity of 40 meters per second at a height of 100 meters above the ground. Where does the package strike the ground relative to the point at which it was released? And what are the horizontal and vertical components of the velocity of the package just before it hits the ground? All right, so you wouldn't want to use the range formula here, right? Even though we're talking about something that we're calling range, because the range formula only applies to level ground. So we just have to come up with a new form of the range formula that is for things that are released at a particular height. Or better yet, just use the kinematic equations, okay? There's only 5 of them. We might as well just use them every time we solve one of these problems, okay? And specifically, I say 5 of them for projectile motion, okay? All right, so find the time in the air. Yeah, see a trend here? Okay, so we're gonna do that by looking at the position function. If we consider our values, we have our final value of y as 0, because we're calling the ground 0. Our initial value of y is 100 meters. Our initial vertical velocity is 0, because the projectile was launched entirely horizontal, because its initial velocity would have been the same as the velocity of the plane. Think relative velocity, all right, because it's relative to the ground. And then our minus 1/2 g t final squared. T final is just the time of, really you can think of this as t final, the total time in the air, or you can think of it as tf, f for flight. So it's the time of flight, okay? I kind of use those terms interchangeably. Time of air, time of flight, they just mean how long the projectile was in the air. All right, so solve for time of flight, right? And we get 4.52 seconds, right? That's how long it takes to be released before it hits the ground. All right, not very long, because things that are truly in free fall move pretty fast, right? Air resistance would slow it down. All right, so then use T air to find the x final equals range. Right, that's just going to be velocity times time, because horizontal motion is really simple for projectiles. It's just constant velocity. So this is 40 meters per second times that time in the air, which is 181 meters. So R is 181 meters, right? So it's not like not like equal side triangles, right? It went further than it was than the height at which it was released, which makes sense. Okay, all right. Well, based on this initial velocity, because it's moving fast. Okay, all right. So then let's find out what is the components of its velocity when it hits the ground, because we were asked for those components. All right. Well, its horizontal component is just 40 because it doesn't change because there's no acceleration in x. What about in the y direction? Right. Well, in the y direction, we're just going to use this kinematic equation of time-dependent vertical velocity, plug in our acceleration and the time, and we get 44.3 meters per second. So it's coming down at almost like a 45-degree angle, right? So if we wanted to find this theta, we just have to do tangent inverse of v final y over v final x, right? Opposite over adjacent. All right. Very cool. Let's mix it up a little bit. Let's have something launched from a higher height than it's going to land at, but instead of being launched entirely horizontally, let's have it launched with a vertical component as well, because that will complicate things. All right. Let's see how that works. Okay. So a little girl throws a ball from her window 8 meters above the ground. When the ball leaves her hand, it is moving 10 meters per second, so we have a speed, and at an angle of 20 degrees below the horizontal. So that means that the initial velocity is going to have both vertical and horizontal components. Use the coordinate system shown in the figure below. How far horizontally from the window will the ball hit the ground? Ignore air resistance. We always ignore air resistance in projectiles because, by definition, they only have an acceleration of gravity. Okay? All right, so first thing we're going to do is we're going to find the components. So we want to find the initial vertical component, and it's negative 3.4, right? Because it's negative 20 degrees, sign of a negative is a negative, and then that's just the hypotenuse of 10. Okay? Now we're not going to immediately find the horizontal component because we don't need it yet. Instead, let's use the vertical component of initial velocity to find the time in the air. Okay? So same darn equation that we used above, right? They both start the same. See? But where before our middle term, so-called linear term, was 0, it's not going to be for our girl tossing the balloon or the ball. So we've got our final height to be -8, our initial height to be 0. That's also just a different coordinate system than the one at the plane, because here we're calling the launch the origin, as before we called the ground at 0. All right. Here is our v naught yt, which becomes negative 3.4 meters per second times t. And here is our gravity term, 1/2 gt squared. All right, and we're going to use the quadratic formula or calculator to find it. So you could use a polynomial solver, you could use a graphing calculator and find the horizontal intercept, or you could just write it out and solve it with the quadratic formula. So you got multiple ways to solve, one of these t squared problems like this. But when we do, we find out that the solution is 0.98 seconds, all right, or at least the positive solution. Okay, so then we can plug that time back into our constant velocity horizontal motion. All right, just plugging in the values. Notice here it's this is going to be v naught x, which is 10 meters per second times cosine of negative 20 again. All right, but by the way, cosine of a negative number, zoom in on this, cosine of a negative number is a positive number, unlike sine of a negative angle. So then that's why we're able to have a positive value here. And then we end up with a positive displacement of 9.18 meters. So that's this distance here. This is r. 9.18 meters, okay? If she had thrown it horizontally, it would have gone further. Throwing it down a little bit shortens the range, all right? How do we know it shortens the range? Well, because we got this negative linear term. All right, so moving on to the concept question. 3 projectiles are shot from the edge of a cliff, all right? Or edge of a table, whatever. I guess it's rock, right? Number 1 with an initial horizontal velocity of 0, number 2 with a small initial horizontal velocity, and number 3 with a large initial horizontal velocity. All 3 have an initial vertical velocity of 0. All right, which projectile hits the ground first? Well, you already saw they all hit at the same time because the initial horizontal velocity will not affect the time in the air at all, And you might say, oh wait, would the time in the air here, was it affected by the initial velocity? Yes, but it was only affected by the initial vertical component of velocity. If you launch this horizontal component, did not affect the time in the air. And if you launch something with only a horizontal component of initial velocity, then it doesn't matter what that velocity is. The time in the air will be unchanged. All 3 of these balls take the same amount of time to hit the ground. Look at the equations, right? And I often say that the idea here is that the motion in x does not affect the motion in y, and vice versa, okay? However, here's something that does change. Which projectile hits the ground with the least speed? Well, that would be number 1, because the final velocity is composed of an instantaneous velocity vector that has components and can be found using the Pythagorean theorem. So we see that if v naught x is small, then v final will be smaller than when v naught x is large. And v naught x is 0 for number 1, so then this term will be the smallest. Okay? All right. Okay, let's look at another example. So this one is the last of the landing on non-level ground ones, or landing at a different height than you started at type of problems, type 2 problems from this lecture. This one is a little bit different because it does actually specify a horizontal distance as well. Okay, so let's see what's different about it. A cannon launches a ball as shown in the figure. The ball lands exactly at the edge of a 135 meter tall cliff as shown, a horizontal distance of 195 meters from the cannon. If the ball spends 7.6 seconds in the air, then what is the initial velocity and angle of launch of the ball? Okay, so we actually have a lot of information, right? We know exactly where the ball is going to land. It's going to land right there, okay? And we know how much time it needs to spend in the air. So all we need to do then is find the initial components of velocity. We need v naught x and v naught y. Okay? All right. So in a sense, there actually is a kind of horizontal restraint on the system. We've specified how far it has to go. I bring that up because it's kind of like a type 3 problem that we'll get into, but it's kind of a bridge between the two. All right, so I'm going to have 2 equations. I'll color code them here. So I'm going to consider the motion in the x direction, the constant velocity motion, and the motion in the y direction, the constant acceleration motion. Okay, so we already know y, y naught, x, x naught, and t. So you already know a lot of the variables. We're only solving for v naught y and v naught x. And the fact we already know t means that it's pretty straightforward. There's no complicated algebra here. All right, so we're just going to take our purple equation here, our motion in x, and solve for v naught x, and take our motion in y, our green equation, and solve for v naught y. So just a single unknown in each equation, just kind of plug and chug them. For v naught x, we got 25.7 meters per second, and for v naught y, we have 55.0 meters per second. All right, and thus, in order to find the speed, the magnitude of vy, we'll just use the Pythagorean theorem, which gives us 61.0 meters per second. And then the angle is just going to be found through tangent inverse of opposite over adjacent, or the vertical component over the horizontal component. And that ends up being 65 degrees. All right? Now, we're not saying that like this thing shoots up and like crashes into the hill, right? Because we specified the time. We're actually finding something that is going to land right there, right? But it probably goes up higher than it and is on its way back down. We can find out whether it's on its way back down, right? But it doesn't matter because we were just asked for this bit of information, okay? But a follow-up question could ask, what is the final velocity, right? And is it moving up or down when it crashes into that particular point that we specified? Okay, well, it depends on the time. All right? Okay, so now let's do a problem where something is going to crash into a wall rather than at a corner of something. So a cannonball is launched from a pirate ship at an initial velocity of 45.8 meters per second at an angle of 25.1 degrees above the horizontal. How fast is the cannonball traveling when it smashes into the mast of a merchant ship at a horizontal distance of 65 meters? Okay, so here the initial information is horizontal distance, whereas we saw before a lot of times it was vertical distance, like with the Alaskan supply drop and the girl throwing a ball out the window. And a similar question that we've seen many times, at what angle does the cannonball hit the mast? All right, so here's the picture, V naught Y, we're crashing into the mast at a particular angle, okay? We don't care how high we hit the mast, we just know that we're going to hit the mast and that is going to stop the projectile, okay? It will no longer become a projectile. So we're going to start with the equation for horizontal displacement, okay, instead of starting with the equation for vertical displacement, like we did in examples 2 and 3. All right, so here we go. And what we're going to do with this equation of horizontal displacement, which is a constant velocity equation, we're going to find the time of flight, just like we would have with the vertical motion equation if the projectile was restrained by a vertical height, right? So that's the idea, right? The restraint is x. Thus, the time of flight needs to be solved from the equation of motion in x. Okay? All right, so find that value, and it's in the air for 1.57 seconds before it crashes into the mast. All right? Then to find the instantaneous velocity at a particular time, we just consider the version of that for y, and then for x, we just know it's unchanging. So in fact, it's just going to be the initial vertical component, or excuse me, the initial horizontal component, which is just 48 or 45.8 meters per second times cosine of 25.1, which, by the way, is just 41.5. All right? Okay, so basically it's just this denominator there. Okay, and then we'll go ahead then and plug in our time of flight into this equation, which we haven't done yet, to find the final vertical component of velocity, and it's 4.07. All right? Oh, wow. So that means that it has a very small final vertical component and a very large horizontal component. So that means it's just by chance, based on the x that we were given, crashing into the mast where it's pretty near the top of its trajectory. It's almost at that point where it's moving entirely in the x direction for one instant in time. All right, so let's go ahead and find the hypotenuse, just the magnitude of v when it crashes into the mast. All right, I bet it's going to be pretty close to 41.5, because when you do the Pythagorean theorem and one of the sides of the triangle is much larger than the other, the hypotenuse is really close in length to the longer side. Yep, indeed, it's 41.7. See, I said really close. It's math is dramatic like that sometimes. To find the angle, we just simply do tangent inverse, just like we did in the problem above. Of course, this is for initial velocity. This is for final velocity. All right, plug in our final velocities, the y component over the x component, and that's because opposite over adjacent would be that angle, or that side over that side, the vertical over the horizontal. And it's 5.6 degrees, right? So it is indeed moving in the pretty horizontal direction. 5 degrees again, kind of like the long jumper, all right? Although round to 6. Let's do another concept question. An elevator is moving upward at constant velocity with a constant acceleration. Oh, wait, that's not a projectile. Well, that's because something will become a projectile soon. Let's read on. The dash curve shows the vertical position of the ceiling of the elevator as a function of time. All right, so here we have the ceiling of the elevator as a function of time, parabolically growing in height as time passes, because it's accelerating upwards. All right, at the instant indicated, right there, by the dot, okay, that's a dot by the way, a bolt breaks loose and drops to the ceiling. All right, from the ceiling to the floor below. Which curve best represents the position of the bolt as a function of time? Okay, so first of all, we know it has to be either option A or B, because since this is the position function of the elevator and thus the position function of the bolt before the bolt starts moving independent of the elevator, the velocity of the bolt at the moment it starts moving independent from the elevator must be the same as the velocity of the elevator. Agree? Well, that means that the tangent line has to be, the initial velocity of the bolt has to be a tangent line of this curve. Well, only A and B are tangent to the curve at the dot. This one is not tangent, this curve is not tangent. Certainly E is not tangent. Okay? So they violate the basic definition of velocity. Okay? So it must be A or B. Well, let's think about this though. Once the bolt is free from the elevator, it's going to become a projectile, which means that its vertical position as a function of time will have to be parabolic. Well, that means the answer is B. All right? Because at the moment of release, V equals delta y over delta t is tangent, as I said, and because it arcs downwards. Okay? That's how we know it's B. All right. So example 6 is just another kind of dropping something from a higher height problem. So I'm just going to kind of go through it quickly. I went ahead and included it because there's a lot going on. There's two separate cases. Case A is basically just the Alaskan drop all over again. You're just going to be solving for x. But case B, part B, is quite interesting because now we actually say, well, what if you want it what if we want the range to be 400 meters? So we're setting that R value. So now our unknown instead is V naught Y. So we're able in the helicopter to launch the package at a certain angle, either above or below the helicopter, and thus have an arcing path that achieves the exact distance that we want of 400 meters. How do we do that? How do we solve for it? And what does it end up being? Okay, so let's just kind of go through this. So in part A, just set up a coordinate system. I'm going to use vertical position to find the time in the air. The time in the air ends up being this expression right here. Then I'm going to plug that back into t. I'm going to plug that t back into the x position function. All right. Here I even go on to say, include plus 1/2 ax a sub x t squared, which obviously isn't necessary because it's just going to be 0. All right. And then we plug that in. Here I'm just plugging in my time. For some reason I left it like this rather than just putting a number in there. And then we get 290 meters. That's our range. Okay. Excuse me. And then in part B, things are a bit different, right? Say the same thing, set up a coordinate system with the origin defined there. Then you can define it anywhere. I just chose to do it there. Okay, we're going to find the time of flight again, but we're going to use the horizontal position to find the time of flight. So it's kind of like the pirate ship, all right? So see, this problem is a mix, right? So I'm going to do that in order to find our time of flight, right? So that ends up being our time of flight expressed symbolically based on the 400 meters and the initial horizontal component of velocity. Okay, and then I'm going to use that time of flight in y motion, plug it back in. Now what's going to be my unknown here? Well, my unknown is v naught y, right? We've seen that before. We saw that with the cannon launching up and landing on the edge of the cliff, right? So we're solving for our unknown of v naught y, all right? But here v naught x cannot change, by the way. V naught x is fixed, right? So the only unknown is v naught y. And we'll solve for it, and plug in all the numbers, and we get 21 meters per second. Now, based on the coordinate system, this sign matters. And since I got a positive value, that means that it is upward. All right? It's not downward. So it's this case because we got a positive there. All right? So that means that it went up. That was the only way for it to achieve is with this particular magnitude of vertical initial velocity and the fact that it's positive was the only way to get it to land exactly where we wanted it, 200 meters below and 400 meters to the side, right there. All right? All right, so it's kind of a cool consideration because you could think of situations where you need to know that. All right. So here's the other type. I have one type of an example here where it's landing on not just another height from where it started, but on ground that has a functional dependence on position. All right. So this is a 30-degree slope. So the idea is we have someone kicking a ball. They're kicking it entirely horizontally. So the initial velocity, graciously, it doesn't have a vertical component, and the slope of the ground is 30 degrees. So how do we solve this? And what are we looking for initially? The first question is how long does it take the ball to hit the ground? So we're solving for time of flight, which kind of makes sense because honestly, if I only asked for part B, you would have had to solve for part A anyway. You would have had to find the time of flight. But here I'm explicitly asking for the time of flight, the time the ball spends in the air before it hits the ground. Okay? Given an initial velocity of 21 meters per second, entirely in the horizontal direction. All right, so how do we do this? So we're going to use projectile motion equations and another equation. Let me zoom in a bit here. We're going to use this equation. This is essentially like a new equation that is specific to this situation where we have a functional dependence between y and x, and it's negative tangent 30 degrees, okay? This is the idea, this is y equals mx, right, where this is our slope, okay? And I found that slope just from the basic definition of, of slope and trigonometry, right angle trigonometry, okay? Well, turns out the tangent 30 degrees, after all, is just a number. It's root 3 over 3, all right? So that means that y equals negative root 3 over 3 times x, okay? That is our line that is the ground, okay? Okay, so then we're going to set up our position function for x, okay? We know v naught x, and we don't really know x exactly, but we do know t, okay? So what am I going to do then? Well, then I'm also going to look at my vertical position function, okay? This one has some zeros. This one also had a zero, by the way. It had x naught, but I zeroed it out and didn't show it. Here I'm explicitly showing that y naught starts at 0. So in other words, this is my coordinate system, right? That's my origin, okay? And my positive is this way and that way. So positive x, positive y. I didn't show it in the figure. All right, and this is just the acceleration, the only thing acting in the vertical direction. Okay, so then I'm going to take these two position functions, these two time-dependent position functions, and plug them in to my functional relationship between y and x. Okay, so I'm putting these in here, see? Okay, so then on the left-hand side, y just becomes, let's see, so, oh, excuse me, I'm putting, this is the left-hand side, I wrote it on the right-hand side, and y just becomes negative 1/2 gt squared, and then this side, the negative root 3 over 3 times x, becomes negative root 3 over 3 times v naught t, because that is x, all right? And notice I dropped the v naught x because v naught x is v naught, because the initial velocity is entirely horizontal. Okay, well now I've got an equation of only one unknown, t. So then I just kind of clean it up a little bit, move it all to one side, so it looks like an equation I can solve with the quadratic formula. And then I solve for t, and I don't show the quadratic formula, but I'm going to say that, I did it in the calculator, I graphed it, right? And I get a time in the air of 2.47 seconds. That's how long it spends in the air. So that's how long it takes before it hits the sloping ground below. Okay, now we know. All right, so then what I want to find how far it goes. Well, now I have the time in the air, it's relatively easy. I can just plug in y equals negative 1/2 9.8 times t squared. So why is it in part B I don't have to take the slope into account again? Because I already have. This time in the air took the slope into account. So then when I answered the question, how far does it go in the vertical direction? What is this value of y, right? I don't need to take the slope into account a second time. Already did. Okay, the time does that, which is pretty neat. Okay, and negative 30. All right, that's how far it goes in the negative direction. All right, I didn't bother to solve for how far it goes in the x direction. You can if you want. All right, so two final examples to wrap up this lecture. These are the two that involve these are the two that involve accelerations that aren't just gravity. So both of them involve horizontal accelerations. One of them involves a non-constant horizontal acceleration, although arguably it's the easier of the two problems. All right, so first example 8. A hot air balloon is rising at a constant velocity of 11 meters per second when a child launches a toy rocket off the side of the balloon's basket. The rocket has a constant thrust acceleration of 2.04 meters per second. If the child launches the rocket at an angle of 20 degrees above the horizontal, and the balloon is at an altitude of 755 meters at the moment the rocket is launched, then what will be the altitude of the balloon when the rocket hits the ground? All right? Wow, right? A lot of moving parts here. So here's the picture. All right, so here is the initial velocity of both the rocket and the balloon. So, really the rocket, that's what we care about most. Here's gravity, because gravity is certainly here. And here's that extra acceleration, the acceleration of the rocket, which has both a vertical and horizontal component. All right, so let's consider motion in the x direction. Right, here it is. Notice that it's not a projectile anymore, so there is a non-zero third term. Okay, let's plug in what we know. All right, so we know that the initial velocity in the x direction is actually 0, right? Because there only is an initial velocity in the y direction. Okay, cool. And the constant horizontal acceleration is just the horizontal component of a naught. All right, because this is, after all, a constant acceleration. All right. And we don't need the x motion for the rocket for this problem, right? This is a great equation, but turns out unless I'd asked something else, you don't need it, right? So let's consider y. Okay, so in the y direction, we've got y equals y naught plus v naught y times t plus 1/2 ay minus g times t squared. Why is this whole thing in the parentheses? Well, this is the net acceleration. There is an upward vertical acceleration, and then there's gravity. Together, they make the total acceleration on the rocket in the y direction. All right, so set this all up. Okay, now we just need to find t, because t is going to be the time of flight of the rocket. Okay, I'm going to use the quadratic equation for that. Here I've just cleaned it up. Then I actually plug it into the quadratic equation, okay, rather than just solving it with a polynomial solver or a graphing calculator. And I get a total time in the air of 14.1 seconds. Rather long time, but that makes sense because the rocket is, after all, accelerating up, partially fighting gravity. All right, and so then in that amount of time, how high does the balloon go? Well, the balloon started at 755 meters, is continuing on its merry way with a velocity of 11, and it does it for 14.1 seconds. So by the time the rocket hits the ground below, and also would have traveled some horizontal distance I didn't ask for, but by the time the rocket hits the ground below, the balloon would have gone straight up and would be now at an altitude of 911 meters. Okay, all right, let's do the last example. A rocket is launched from a height of 30 meters. The initial velocity of the rocket is 12 meters per second, okay? The rocket's engines produce a horizontal acceleration of 1.6 meters per second cubed times t. So here we have a linear acceleration. Okay, I point out it's non-constant. Okay, the direction of the initial velocity is horizontal. Okay, so that this 12 meters per second is entirely in the x direction. In the vertical direction, the acceleration is just g as normally. Drag is ignored. What horizontal distance does the rocket travel before hitting the ground? All right, so here's our picture. This is the rocket launching off the ledge of something. Okay, all right. The ground below is 30 meters below. All right. So what we're going to do is we're going to find a position function in x. We're going to do that using integral calculus. All right. T is the time in the air, so we're integrating from 0 to t. So t is the time that we're interested in. All right. So let's go ahead and consider what that looks like. Oh, and then also a similar integral for velocity. Okay. Okay, looks good. Okay. And so then I've got, when I do the integral for velocity, I start with my acceleration function, which is just 1.6 times t. Okay, and I'm just going to integrate it from 0 to t, so definite integral, but my upper limit of integration is a variable. All right, and the time spent in the air is found with the y motion. Okay, so let's look at that. So we've got y equals y naught plus v naught y times t minus 1/2 gt squared. Because in the y direction there is no acceleration, so it's just we can just go back to treating it like a projectile. All right, and so we got 30 minus 1/2 times 9.81 meters per second squared times t squared. Solve for t. All right, so the time it spends in the air is 2.47 seconds. So now with that information, we're going to go back and consider the integrals I wrote above. All right, so if I go ahead and solve for vx by solving this integral and doing the rules of antiderivatives, I'm going to get 1.6 over 2 times t squared. Okay, that's just from doing the antiderivative there, plus 12. Why 12? Well, because that was my initial velocity was 12. Right, so there was a plus v naught over here. Right, excuse my bad notation. I wrote this a while ago. Probably could use a rewrite. All right, and then we're going to do the same thing for x. Okay, and for x, I'm just going to take that integrated the second time as shown up here. All right, and that's where we get a 1.6 over 6 because when we do the antiderivative rules again, our t cubed means we have to be dividing by 3, which means now we're dividing by 2 times 3 or 6. Okay, and then my constant term, the initial velocity in the horizontal direction, becomes 12t. Okay, so t cubed, 12t. All right, and 1.6 over 6, t cubed plus 12t. Why is there no other term? Why is there no constant of integration here? Well, that's because we're calling this x naught. Okay, all right, looks good. And then it's just a matter of plugging in the t into this equation. We don't have to solve this equation, which we could solve graphically, although there's no quadratic formula for third order polynomials, but we could solve it graphically. But we don't have to. We just plug in our t and get our value of x, and it's 33.7 meters. That's how far it goes before it hits the ground. All right, and that's it. That's our final example, our big exploration into projectile motion and things that are like projectile motion. Hopefully all of these examples were very helpful and really showed you techniques in solving these problems. Thank you so much for watching this video, and stay tuned for more from Chapter 4.